given that there were a lot of talks before me and they probably synthesize what I'm saying, I will try to go pretty fast. This is the work that we have been doing with Eric Howdy at DGM, James Van Orman at Case Western, and Mark Rutherford here at Brown. And the computer is not working. What do I need to do then?
Sorry, it just wasn't.
Okay, so the reason that we care about the moon is, I think, because with the moon we can get a frozen record of the first 500 million years of the solar system formation, especially for the volatiles and the delivery of volatiles to the Earth and Moon. In 2008 we presented the first evidence, and we show a profile of concentration that indicated that the water and other volatiles were indigenous to the moon. In 2011, we show, based on the study of melt inclusions, that the concentration of volatiles that we see are equivalent to those that we found in mid-ocean ridge. And you can see in this figure a picture of the melt inclusion from Apollo 17, and then fluorine, sulfur, and chlorine versus water content, where the orange dots with the dark rims represent the melt inclusions, the orange dot on the left side without the black rim represent just glasses, and the gray field represent the composition of volatiles for mid-ocean ridge basalts. So the question came up of where the water come to the moon, and from where the water come to the moon and when. And in general, the age ratio, as most of you know, has been used as a tracer of the source for the water, and in here you have a diagram for the different planetary bodies, and you have many planets, then you have carbonaceous chondrite, the Earth, Mars and Mars atmosphere, Venus atmosphere, the Oort cloud comets, and the Jupiter family of comets that were analyzed not that long ago. So there is large variability in the DH ratio, and that's what we wanted to do to determine the source. And there was a paper by Greenwood, and now more papers are appearing, where it shows that most of these apatite seems to have not only high water content, but also high delta D. And the interpretation from Greenwood was essentially that most of these represented the influence of Oort-type comets as a delivery process for the water to the moon. The problem that we have with this, the study of apatite, is that it's very difficult to determine the previous history of the magma, either crystallization, degassing, and furthermore is the problem of impacts. So you have solar wind implantation and later impacts that was demonstrated by Liu et al. 2012. So there are several complications of the apatite. So our best approach was to try to use the most primitive samples that we can get from the moon, which are the lunar volcanic glasses. And this is the result that we published this year. And essentially, this is what we measure. And I want you to pay attention. The colors, essentially the green colors that you see will be the green glasses from Apollo 15. The yellow colors are yellow-brown Apollo 15 glasses, and then the orange colors are the Apollo 17 high titanium glasses. The different symbols are, for the orange glasses, you will see glasses which are square. The diamonds represent matrix glass that are surrounding the olivines, and the circles represent the composition of the melt inclusions. So when we use DH, the DH is not only source indicator, but it's also process indicator. To backtrack all the processes to come up with the original DH, we need to consider what processes could affect. One of the most important processes are spallation. Here is the same data corrected, and you can see that a lot of the inverse correlation between DH and the water content now disappears or is decreased. And this was done just by taking the exposure ages for the Apollo 17 of 30 million years from Oyster. And then you have, for Apollo 15 glasses, 300 million years for Spangler. And then we use the production rates for deuterium from Merlibat, 1976, and the experimental data from Reedy, 1981, and for hydrogen, for the data from Yokoyama and Covalent, 1976. So even if we consider that, we will see that we need to consider another process. So spallation is a process, and the second process is degassing. We cannot consider equilibrium degassing or Rayleigh fractionation, and we cannot consider that because if you see the composition of, for example, water on the glass bead, you see a variation with distance from the core to the rim, which indicates that it's probably kinetic degassing. So in order to deal with this, we consider just simple kinetic degassing. It's essentially a 1D spherical diffusion equation that we took from McDougall and Harrison. And essentially is that the ratio of the diffusivity of hydrogen to deuterium is in some ways related to the difference in the mass of deuterium and hydrogen and a beta exponent factor, which this has to do with the speciation. And when we do this calculation, there are many unknowns on this because we lack significant amount of experimental data. And also we know by the work that Mark Hirschman has done that the amount that you have of a species like H2, water, or OH will depend on the water content, the fugacity of oxygen, and the temperature, and so forth. So the values that we can, it's just, this is the best thing that we can do with different beta value. The first beta value is around 0.5, which is essentially considered the theoretical value. From 0.29 to 0.12 is if we assume the beta value for what we estimate is the diffusivities for H2 or HD. And then you have in green, which is a beta value from 0.039, 0.016, which is for OH, for water. And then you have beta values from 0.015 to 0.007, which are in blue dashed lines, which are the beta value for OH. The one that we put in there in orange, the line orange of a beta value of 0.06, is the highest that we can estimate empirical from the data that we obtain. The strong orange represents the values corrected for spallation because these values, you can see that they have a very, very large error on the estimation, not only on the age, but also on the production rates. I also put in light colors, light color orange, the values that we measure. So for the values that we see, the beta value would indicate that it's between H2 and water diffusivities. The most likely scenario is that you have a change as the degassing proceeds from going from H2 type of degassing to OH at the end. In any case, when we consider all that, the values that we can assume are the most primitive are the values of the melt inclusion, that given the low exposure to cosmic rays and the high concentration of water, they were very little affected. We cannot assume that these samples didn't suffer degassing before the entrapment of the melt inclusion. Therefore, the melt inclusion value give us a upper value for the DH and a lower value for the water content. So if we put that value with the diagram that we saw before, you see now what we consider the most primitive value for the DH of the moon, and it's essentially consistent with chondrites, and it's close to Earth. We don't know if the values that we got represent the actual DH of the primitive moon, but it's close enough. Either if this is the primitive value, it would represent that something happened during the formation of the moon compared to the Earth, and it got a little bit higher. Also, the budget for the Earth, if we, depending who we believe for the water content, compared to the moon, it could be a factor of 5 to 10 lower for the moon. So it could easily indicate that we didn't essentially sample the most primitive values for the moon, or that the moon has lower water and slightly higher DH than the Earth, but not significant compared to the whole variation, and certainly is not related to all cloud comets. Now, someone like showed before, I believe by Lindy, it says that the Jupiter family of comet it could be an issue, but then when you plot the nitrogen isotope, indicates that not even that will match. The problem with the comets is that we sample only the coma aspect, mostly by remote sensing. We don't have a full composition of the comet. There are organic composition, and there are some species that are not seen spectroscopically that we cannot know what are the different DH or nitrogen isotope. But there, if you put the values for the Earth and Moon, you can see that they look very similar and within the chondrite values. So the question is how it arrived. Well, there are two possibilities, and these need to be, they arrive very early, the volatiles to the Moon arrive very early. One possibility is the late veneer, but if we look at the platinum group elements, we will see that there is almost no effect of the late veneer on the Moon, and therefore we discard that possibility, and therefore the only possibility that we have left is that just the water came from Earth during the giant impact, and this will require the models that Steve Tesh and Jeff Taylor are trying to do, and Palevan are trying to do, to try to understand how hydrogen will be preserved, at least partially, in this giant impact. The other thing that I think that we should consider is that there could be a less processed lunar reservoir in the interior, and this might be in the observation that have been presented lately by the Grail that uses Andrews Anna observation that there have been some extension that tell us that there was essentially a cold core at the beginning of the formation of the Moon, that you might have slightly extension today. I believe this between 1 to 4 kilometer extension, and that indicates that the whole Moon might not have been completely molten, but you have a cold core that as the shallow magma ocean, maybe 400 kilometers, is cooling, you begin to heat the core. If we have that core that is a less processed lunar mantle, maybe part of the water that we see come from that. And the conclusions, well, I guess in the last 5 years, we showed the first evidence for the water. We showed that the water amount is equivalent to MORP. And now we said that essentially it's carbonaceous chondrite, but most likely it's coming from Earth. That means that the Earth had the water in it before the impact. So that means that the water came to Earth during the Earth's accretion, and this is consistent with dynamic models presented by Kevin Walsh and Morbidelli and others, Raymond. And I think that if we consider that the values that we see for the Moon are essentially the values that there was in the system at the initial stages of the Moon formation, and we see that there is no significant variation. Yes, within a factor of 5 for the water budget, and the DH is slightly different. We can say that essentially the water for Earth didn't change much since the formation of the Moon. I think that that's one of the most important implications that could come from the work that we are doing right now. It's about the water on Earth. Thank you very much.
Thank you, Alberto. So we do have some questions for you. We've got a question from Mahesh Anand. Elaborate as to which process, apart from degassing, can fractionate deuterium from hydrogen in the lunar magmatic system?
Well, it's what we said. I think more than the fractionation, depending on what temperature you do it, if you consider this high temperature, then I would say that degassing probably the most important. But then it's the spallation. And the spallation, people said, well, we don't find spallation with cosmic ray exposure. But we need to consider also that the same exposure to different samples that have different water content initially will have a different effect. For something that didn't have much water at the same exposure, you will have a much more effect on the DH than if you have a sample with high concentrations of water at the same type of exposure. So those are the things that we need to clarify when we need to correct for the spallation processes.
Okay, there's also a question from Rishitosh. What physical boundary is there to separate less processed lunar mantle with the so-called process?
Well, I'm not sure exactly exactly what this means. When I said, I think that one way is how to preserve, what I'm trying to figure out is how to preserve the hydrogen. And the hydrogen is the most volatile element. And in order to preserve it, one of the ideas was, if you think that there is an impact and some piece of the earth comes out and it probably was molten, but you can quench it really quickly. And over that less processed earth type of material, you begin to continue accreting what is in the lunar disk. Maybe there is a way to preserve the water and the DH. That's all what I can say. And then we go back to the work that Solomon did, right? That they said, well, if you will have a full magma ocean, you will see high compressions on the surface. And he says that the most likely scenario is that we don't see that, and therefore you have a core of the moon that it was cold. And then you accreted and you form a shallow magma ocean. And now with the Grail data that essentially shows these extensions based on the gravity, which indicates probably intrusion of mafic material, which is roughly equivalent to what John Solomon said in 1976. I think it's a very good evidence that we need to consider processes like this, like John Solomon said, that you could have an initial core unprocessed or less processed. That will help a lot, given the composition. One of the problems that we have with the moon is how we make compatible the physics of formation of the moon by the giant impact with the chemistry that we are seeing is essentially equivalent to Earth. Yes, with some difference in the volatile elements, but mostly equivalent to Earth.
Okay, looks like we have another question for Alberto. How do you extrapolate the calculated abundance of OH, H2O that was the source of the volcanic glasses to that of the bulk moon's water budget?
I cannot see. Which one is that?
That's George Kramer.
George Kramer. How do you extrapolate the calculated abundance OH that was in the source of the volcanic glasses to that of the well, if you put, it's hard to extrapolate clearly. We need more data. The problem is if you put all the data together, if you consider the appetite values that people are finding, the values that we see in the lunar glasses, the consideration of the gassing, I think that we can easily establish that a conservative value will be around 100 ppm in the source. Clearly, more data we have, more data will confirm this or disprove this. But there is no other way to do. Right now, just if we consider just simply for the orange glasses or the green glasses, and we assume that they have around 1,000 ppm or so in them, if you assume that it's a 10% extent of melting of a lunar mantle, like John Longy has calculated, you finish with around 100 ppm in the mantle source of these things.
Okay, I think we have one more question for Alberto, and then we'll open it up to the larger discussion. But Jessica Barnes has a question. In Mare basalt, apatites that have over 6,000 ppm OH still have delta Z of more than 500 per mil. She wonders if this cannot be ascribed to spallation.
Well, that will depend on how long you expose them, right? Probably not at that concentration. I would say that at that concentration, probably the spallation will not be the most important things that you should consider. That will be my guess. The question is how much fractionation there was. So if you think that the apatites will come at, I don't know, after 95, 96% or 98% crystallization, and then using some partition coefficient for water between apatites and melts, you can calculate roughly how much was the water that was initially in it. But also you need to consider